You wake up this morning, and the third visitor from another star system is streaming live through telescopes in Italy. Not a theory, not a simulation. Actual photons bouncing off something that formed around a different sun billions of years ago, traveling through your screen right now. The hype says alien mothership. The panic merchants say doomsday rock. But strip away the noise, and what you get is harder, colder, and way more interesting than either fantasy. 3, because it is the third confirmed interstellar object humanity has ever detected passing through our solar system. I for interstellar, meaning it does not orbit our sun, it is just passing through on a hyperbolic trajectory that will slingshot it back into the void. Atlas, because the robotic telescope array in Rio Hurtado, Chile, spotted it first on July 1st, 2025, when the object was 670 million kilometers from the sun, cruising through the orbit of Jupiter at 1,000 kilometers per hour. That is not star travel speed. That is what billions of years of gravitational kicks from dead stars, nebulae, and rogue planets will do to a chunk of ice and rock drifting through interstellar space. By the time Atlas flagged it in their nightly sweep, pre-discovery images from the Zwicky Transient Facility and 3 other Atlas stations worldwide had already captured it, going back to June 14, 2025. Nobody noticed because it looked like 17,000 other faint dots that crossed the sensors every night. What made astronomers double-check was the speed and the angle. Objects bound to our sun follow elliptical paths. This thing was on a one-way ticket out. Within 48 hours, follow-up observations from the Nordic Optical Telescope, the Canada-France-Hawaii Telescope on Mauna Kea, and the Deep Random Survey in Chile all confirmed a faint coma and a potential tail-like elongation 3 arcseconds. Long, that glow meant gas and dust venting off the surface, not an asteroid, a comet. On July 2nd, 2025, the Minor Planet Center issued the official interstellar object designation 3I, making it only the third in recorded history after 1 I Oumuamua in 2017 and 2 I Borisov in 2019. By the time the announcement went public, astronomers had logged 122 separate observations from 31 observatories across 6 continents. Every telescope that could pivot was already watching. If you value documented interstellar physics and real-time comet tracking like this, subscribe. It is the best way to support our work. Also comment from which city you are hearing this from. Also, this script is researched and factual using sources from NASA's official Comet 3 iAtlas mission page, updated November 14, 2025, the European Space Agency's ExoMars Trace Gas Orbiter Observation data, published October 7, 2025, Wikipedia's 3I Atlas article with references through November 17, 2025, with over 250 citations to peer-reviewed journals, the SkyLive's real-time ephemeris data, and the Hubble Space Telescope Imaging Study by David Jewett and team published in the Astrophysical Journal, Letters, August 7, 2025. Now back to the information. The live stream starts at 11:15 p.m. Eastern Standard Time tonight, November 18, 2025. That is 4:15 a.m. Greenwich Mean Time on November 19th. The Virtual Telescope Project in Manciano, Italy will aim their robotic telescope array at the constellation Virgo, where 3I Atlas is currently drifting across the pre-dawn sky at magnitude plus 10.9. Too dim for your eyes. Too dim for binoculars. But bright enough for any decent backyard telescope with an 8-inch aperture to resolve as a fuzzy blob against the sharper stars. Gianluca Massi and his team will stream the feed live on YouTube. No subscription. No paywall. Just raw telescope data bouncing through fiber optic cables so anyone with an internet connection can watch a visitor from another star system in real time. The event was supposed to happen November 16th, but clouds rolled in over Tuscany. Weather permitting, tonight it happens. 3. iAtlas has been behind the sun from Earth's perspective since late October, invisible to ground-based telescopes during the exact window when it hit perihelion, its closest approach to the sun, on October 29th and 30th at 1. 0.4 astronomical units, or 210 million kilometers, just inside the orbit of Mars. During that critical pass, when solar heating should have ramped up outgassing and tail formation to peak visibility, only spacecraft at Mars got a clear look. ESA's ExoMars Trace Gas Orbiter and Mars Express captured it on October 3rd at a distance of 30 million kilometers. China's Tianwen-1 Mars orbiter snapped images the same day. NASA's Mars Reconnaissance Orbiter used its high-rise camera to photograph 3I Atlas with a resolution of 30 kilometers per pixel, 3 times sharper than the Hubble Space Telescope's best shot from July 21st when the comet was 4. 146 million kilometers from the Sun. Those high-rise images sat locked in NASA servers for over 40 days due to a US government shutdown that froze non-essential data releases. Congressman Anna Paulina Luna from Florida sent an official letter to NASA demanding the images be made public, arguing the data is time-sensitive as the comet fades and recedes. The shutdown ended. NASA scheduled a live press conference for 3 p.m. Eastern on November 19th to finally release those Mars orbiter images, along with observations from multiple spacecraft, one day after the virtual telescope livestream. 2 chances to see 3 I-Atlas, one from amateur astronomers in Italy with consumer-grade equipment, one from NASA's fleet with billion-dollar optics, both happening within 24 hours. What you're looking at when you watch that stream is not just a comet, it is a sample box from somewhere else. The Milky Way galaxy contains an estimated 200 billion to 400 billion stars. Most formed billions of years before our sun ignited 4.6 billion years ago. When stars die or planetary systems go through violent reshuffling, they eject debris, comets, asteroids, planetary fragments, Kuiper Belt leftovers. All of it drifting through interstellar space at speeds anywhere from 10 to 100 kilometers per second, depending on the gravitational history. Our solar system plows through this debris field as it orbits the galactic center at 220 kilometers per second. Most interstellar objects miss us by light years. Some get close enough for our sun's gravity to bend their paths into detectable hyperbolic arcs. 3 I-Atlas is one of those rare intercepts. Hubble space. Telescope observations on July 21st, 2025 pegged the nucleus diameter somewhere between 440 meters and 5.6 kilometers. That is a huge range because the nucleus sits buried inside a glowing coma of gas and dust that makes it appear brighter and larger than the solid core actually is. High-resolution images from the Gran Telescopio Canarias on July 2nd showed the coma spanning 26,400 by 24,700 kilometers, roughly twice Earth's diameter. But the coma is optically thin, mostly transparent carbon dioxide gas mixed with dust grains. The actual nucleus could be as small as a single city block or as large as a mountain range. The uncertainty drives astronomers crazy because size determines mass, and mass determines everything else. How much material can it shed? How long will it stay active? What is the composition breakdown? Harvard astrophysicist Avi Loeb calculated that if the nucleus is truly 5.6 kilometers across, the energy output and jet activity observed during perihelion exceed what standard sublimation physics can produce from an object that size. If it is closer to the lower estimate, around 1 kilometer, the numbers work better, but raise different questions about why it appears so bright. NASA's Transiting Exoplanet Survey Satellite, TESS, observed 3 I-Atlas before anyone knew it existed. Archive images from May 7th to June 3rd, 2025, when the comet was 6.4 astronomical units from the Sun, showed it was already bright and active. Water ice sublimates at distances closer than 3 astronomical units. Carbon monoxide starts around 5. Carbon dioxide can go active even farther out in the deep freeze. TESS data proved 3 I-Atlas was venting gas when it should have been dormant, suggesting its composition leans heavily towards supervolatiles that react to even faint sunlight. Follow-up spectroscopy from NASA's James Webb Space Telescope on August 6, 2025, using the near-infrared spectrograph, and from the SphereX Space Observatory during mid-August, confirmed massive amounts of carbon dioxide. 87% by mass, carbon monoxide at 9%, water making up most of the remaining 4%, trace amounts of hydrogen cyanide. And nickel vapor without iron, detected at distances 4 times farther from the Sun than Earth, where temperatures should be too cold for metals to vaporize. Thomas Puzia at Pontificia Universidad Católica de Chile led the team using the very large telescope in Chile's Atacama Desert that caught it first. His student Rohan Rahat-Gonkar was set to observe 3 I-Atlas through the Southern Astrophysical Research Telescope when they spotted emission lines matching nickel at wavelengths that do not lie. As the comet closed in on the Sun over multiple observation nights, nickel levels increased while iron stayed absent. In industrial chemistry on Earth, nickel without iron happens through the carbonyl process, where carbon monoxide reacts with nickel at specific temperatures to form nickel tetracarbonyl gas. That is a human-invented technique. Seeing it in a natural comet from another star system means either the chemistry of interstellar space runs similar reactions, or 3 I-Atlas picked up its composition from a planetary system with very different formation conditions than ours. No one is sure which, but the data published by Puzia's team in August 2025 in a peer-reviewed paper submitted to the Astrophysical Journal does not lie. Nickel is there, iron is not. That breaks the usual pattern for solar system comets where both metals show up together in roughly solar abundance ratios. 3I Atlas entered the inner solar system aligned almost perfectly with the ecliptic plane, the flat disk where all the planets orbit. The odds of a randomly oriented interstellar object hitting that narrow band by accident sit around 1 in 500. Loeb has pointed this out repeatedly in blog posts and interviews since July, noting it could mean the object's path was influenced by a massive gravitational encounter billions of years ago that happened to funnel it towards star systems with planetary disks. Or it could mean something else. He does not commit to the something else in print, but he does not rule it out either. What he does commit to is data collection. On October 3rd, when 3I Atlas passed Mars, Loeb coordinated with international teams to ensure every available instrument captured spectra, imaging, and positional data. The European Space Agency's Planetary Defense Office used the Mars flyby observations to refine the comet's trajectory by a factor of 10, narrowing the uncertainty envelope from thousands of kilometers to hundreds. That improvement matters for future missions. If another interstellar object comes through and we want to send a probe to intercept it, knowing exactly where it will be 3 months ahead, instead of roughly where it might be, is the difference between mission success and a billion-dollar miss. ESA is already planning for that scenario. Comet Interceptor, scheduled to launch in 2029, will park itself in a Lagrange point orbit and wait, not for a specific target. Just wait until astronomers spot the next interstellar visitor or pristine Oort cloud comet making its first pass through the inner system. Then it will fire its engines and chase. The mission was designed before 3I Atlas showed up, back when only Oumuamua and Borisov were known. Now, with 3 confirmed interstellar objects in 8 years, the odds look better that Comet Interceptor will actually get a chance to fly. Michael Kuipers, the mission's project scientist, said in an October interview that visiting an interstellar object could provide a breakthrough in understanding their nature, especially since all 3 so far have shown large diversity in appearance and behavior. Oumuamua accelerated away from the sun without visible outgassing, leading to theories about solid hydrogen icebergs or even light sails. Borisov looked exactly like a normal comet. 3. I Atlas sits somewhere in between, showing cometary activity but with chemical ratios and energy outputs that do not fully match either category. The Virtual Telescope Project's live stream tonight gives amateur astronomers and casual skywatchers a front row seat to watch this weirdness unfold in real time. Gianluca Massi, who runs the project, captured 3I Atlas on November 6th, 10th, and 11th from his station in Menciano. His November 11th image showed the ion tail stretching at least 0.7 degrees, roughly 1.5 moon widths, pointing northeast, while an anti-tail extended east-southeast. Anti-tails happen when Earth's viewing angle crosses the orbital plane of the comet, and we see dust particles lagging behind the nucleus, creating an optical illusion of a tail pointing toward the sun instead of away. But 3I Atlas has shown anti-tail structures in multiple observations, including the Hubble image from July, where the tail extended sunward when solar radiation pressure should push everything away. That geometry suggests either the dust is much heavier than typical comet ejecta, sinking back toward the nucleus under weak gravity, or jets are firing in unusual directions. The Mars spacecraft data might clarify which when NASA releases it tomorrow. Also, this script is researched and factual, using sources from Space.com's November 17th article on the livestream written by Anthony Wood, the BBC Sky at Night Magazine's November 17th coverage by Ian Todd with detailed finder. Charts for Virgo, Avi Loeb's series of Medium articles from September through November 2025, analyzing high-rise expectations and nucleus size calculations, and the SETI Institute's Comet 3I Atlas Perihelion update published by Dr. Frank Marcius, documenting unistellar network brightness observations. Now back to the information. The SkyLive's real-time tracker places 3I Atlas at approximately 342,767,000 kilometers from Earth, passing through Virgo. Its apparent magnitude has faded to around plus 10.9 as it moves away from the Sun and Earth simultaneously on its hyperbolic escape trajectory. Right now it is traveling at roughly 246,000 kilometers per hour, the speed it gained falling toward the Sun, minus the deceleration as it climbs back out of the gravity well. When it leaves the solar system entirely, probably sometime in late 2026, after passing Jupiter at a distance of 54 million kilometers on March 16th, it will settle back to the same velocity it entered with, 221,000 kilometers per hour relative to the Sun. From there, the journey continues. Where it goes depends on the local gravitational landscape of nearby stars. Simulations run backward from its current trajectory suggest it has been drifting for billions of years, possibly 10 billion or more based on its reddish color caused by cosmic ray bombardment, converting surface organics into complex tholins. That reddening matches the color of Kuiper Belt objects and trans-Neptunian bodies that have been frozen in the outer solar system since formation. But 3I Atlas got that dose of radiation in interstellar space, between stars, where temperatures hover just a few degrees above absolute zero and ionizing particles from supernovae, stellar winds, and cosmic ray showers sandblast any exposed. Surface. No drama, just a distant fuzzy dot to backyard telescopes. After that, it fades. By March, when it crosses Jupiter's orbit, magnitude will drop below 15, beyond the reach of most amateur equipment. Professional observatories will track it as long as they can, but eventually it will vanish into the noise, one more faint speck among billions. The difference this time is we caught it early. July discovery gave astronomers 5 months to coordinate observations before perihelion. Hubble, Webb, Swift, TESS, SphereX, ground observatories in Chile, Hawaii, Spain, Italy, and the Canary Islands all logged data. Mars orbiters grabbed close-ups during perihelion when Earth-based telescopes were blind. The Vera Rubin Observatory, still in science validation mode when 3I Atlas was discovered, caught it in archival images from June 21st to July 3rd, showing the coma diameter, growing from 13,040 kilometers to 18,760. Had Rubin started its validation runs 2 weeks earlier, it would have beaten Atlas to the discovery. Hubble is scheduled for additional ultraviolet spectroscopy to measure sulfur to oxygen ratios in the outgassing. Webb has another observation window in December after perihelion to see if the composition shifts as the comet cools. ESA's Jupiter Icy Moons Explorer, JUICE, currently on its way to Jupiter, attempted observations in November from its unique position closer to the Sun. The spacecraft is using its main high-gain antenna as a heat shield right now, limiting data transmission rates, but if it captured anything useful, that data will trickle back over the coming weeks. Every data point matters because interstellar objects do not come back for a second look. Once 3I Atlas exits the solar system, it is gone. The next one could arrive next year or in 50 years. No way to predict. That is why tonight's live stream and tomorrow's NASA press conference carry weight. Not hype, not speculation. Just documented observations of something we will never see again. Composition tells us what interstellar space is made of, or at least what survives billions of years drifting through it. Activity rates tell us how much energy input triggers outgassing and at what distances. Nucleus size constrains models of planetary formation and collisional evolution in other star systems. Trajectory refinement improves our ability to predict future encounters and plan intercept missions. Spectroscopy reveals chemistry that might match or differ from solar system norms. Every measurement feeds into the larger question astronomers actually care about, which is not are we alone, but what are the physical conditions and material inventories of planetary systems across the galaxy? 3I Atlas is a sample return mission that returned itself. We just have to read the label. Oumuamua blitzed through in October 2017, discovered by the Pan-STARRS telescope in Hawaii 13 days after it had already passed perihelion and was heading back out. Astronomers had maybe 2 weeks of viable observation time before it faded beyond detection. No coma, no tail, just a tumbling elongated object accelerating away from the sun faster than gravity alone could explain. That non-gravitational acceleration sparked endless debates. Comets do it all the time through outgassing jets, but Oumuamua showed no visible jets. Loeb proposed radiation pressure on a thin, artificial light sail as one possible explanation that fit the acceleration profile. Other scientists suggested a hydrogen iceberg, a solid chunk of frozen molecular hydrogen that would sublimate without leaving a visible trail because hydrogen scatters light poorly. Still others argued the shape was misinterpreted, and it was actually a fluffy aggregate that broke apart under tidal stress, changing its mass distribution and apparent acceleration. 8 years later, no consensus. The data ended when Oumuamua faded below magnitude 27 and left the observable universe. Caught inbound at 4 astronomical units, it stayed visible for months as it swung around the sun and left. Spectroscopy showed water vapor, carbon monoxide, and dust ratios consistent with solar system comets. Hubble images revealed a nucleus around half a kilometer across, shedding dust at normal rates. No anomalies, no mysteries. Just a comet from somewhere else behaving exactly like comets from here. That consistency actually told scientists something valuable. Whatever process forms, comets around other stars produces results similar to our own Kuiper Belt and Oort cloud. Chemistry is chemistry. Ice is ice. Gravity is gravity. The laws do not change based on address. But the nickel without iron, the early activity at 6 astronomical units, the possible nucleus size discrepancy, the aligned trajectory, the anti-tail geometry, and the energy output calculations that do not quite balance all add up to a profile. That is normal enough to call it a comet, but weird enough to keep asking questions. That is where good science lives, not in the clean answers, but in the edge cases that force you to refine the models. Virtual Telescope Project uses robotic mounts that automatically point and track based on ephemeris data pulled from JPL Horizons, NASA's Solar System Dynamics database. Coordinates for 3, I-Atlas, get updated constantly as new observations refine its position. The telescope locks on, opens the shutter, and integrates light over exposure, times ranging from a few seconds to several minutes, depending on sky conditions and target brightness. The raw frames get stacked to reduce noise, then streamed live with minimal processing. What you see is what the sensor sees. No artistic enhancement, no false color unless specified. Just photons collected from an object currently 246 million kilometers away, traveling at 68 kilometers per second relative to Earth. The light hitting the telescope tonight left 3 I-Atlas roughly 13.5 minutes ago. If the comet suddenly exploded right now, we would not know for another 13.5 minutes. That light delay is not dramatic at interstellar scales, but it is real enough to matter when you're trying to coordinate observations across multiple ground stations and spacecraft. The moon is currently waning gibbous, almost full, which normally kills faint object observation, because scattered moonlight floods the sky and drowns dim targets. But 3I Atlas is far enough from the moon's position in Virgo that Massey's images from November 6th, 10th, and 11th all resolve the comet despite lunar interference. His November 6th shot was taken with the moon just 10 degrees away and only 12 degrees above the horizon. The fact that the coma and tail showed up anyway means the signal is strong enough to punch through less than ideal conditions. Tonight should be clearer, moon farther, sky darker, better seeing. The stream should show real-time motion if the exposure cadence is tight enough. 3 I-Atlas moves roughly 0.1 arcseconds per minute against the background stars. Not visible in a single frame, but obvious in a time-lapse sequence over 30 or 40 minutes. Stars stay fixed, comet drifts. That drift is your proof it is not part of the background. It is a visitor passing through. Viewer expectations should stay realistic. This is not going to look like a glossy NASA press photo. It will look like a fuzzy gray blob, slightly elongated if the tail is prominent, moving slowly across a field of white dots. The excitement comes from knowing what you are looking at. That fuzzy blob is shedding gas and dust in real time as frozen carbon dioxide sublimes under weak sunlight, 210 million kilometers from the heat source. The tail stretches hundreds of thousands of kilometers behind the nucleus, maybe more, depending on how much material perihelion kicked loose. Ion tails driven by the solar wind can extend millions of kilometers on comets with strong activity. 3. I-Atlas is not particularly active compared to great comets like Hale-Bopp or McNaught, but it is active enough. The glow you see is sunlight scattering off dust grains and fluorescing off ionized gas molecules. Carbon monoxide ions emit in ultraviolet. Carbon dioxide fluoresces in infrared. Water produces hydroxyl radicals that glow in visible wavelengths. The mix determines the color. Most comets look greenish in long exposures because of diatomic carbon emission bands, but 3 I-Atlas has appeared more reddish or neutral in color images due to its dusty coma and tholin-rich surface. NASA's press conference tomorrow at 3 p.m. Eastern will release the high-rise images that have been locked up since early October. Spatial resolution of 30 kilometers per pixel means if the nucleus is 5 kilometers across, it will show up as a single bright pixel, or possibly 2, depending on the exact orientation and exposure settings. If it is smaller, it will not resolve as an extended object. But the brightness of that central pixel will tell astronomers exactly how much light is coming from the nucleus versus the coma. That measurement pins down the size estimate better than Hubble managed because HiRISE had a side-angle view while Hubble was looking almost directly along the anti-tail axis. Different geometry, different information. The coma size will also be measurable in the HiRISE frames. If it had grown or shrunk significantly between July and October, that tells you how the comet responded to perihelion heating. If jets are visible, their direction and intensity map the nucleus rotation and active vent locations. All of that comes from a few dozen pixels in a single set of images taken 43 days ago. But those pixels matter, because they are the best close-up we are going to get unless someone figures out how to build and launch an intercept mission in the next 6 months, which is not happening. China's Tianwen-1 also photographed 3 I-Atlas on October 3rd from 30 million kilometers using its high-resolution imaging camera, HiRIC, with a 50-centimeter aperture. Those images were released publicly in early November, while the HiRISE data stayed classified behind the US government shutdown. High-RIC images showed the nucleus and coma spanning several thousand kilometers, consistent with ESA and Hubble observations. No major surprises, but also no fine detail because high-RIC has lower resolution than high-rise. Still, the fact that China released their data immediately while NASA sat on theirs for political reasons did not go unnoticed in the astronomy community. Avi Loeb called it out multiple times in blog posts and media interviews, arguing that science should not wait for bureaucracy, especially on time-sensitive targets. Congresswoman Luna agreed, and pushed hard enough that NASA scheduled the release. Whether the images show anything groundbreaking or just confirm what everyone already suspects, a normal comet with slightly unusual chemistry, remains to be seen, but at least they will be public. The broader context here is that humanity is entering a new phase of interstellar object detection. The Vera Rubin Observatory, when it reaches full operational capacity, will scan the entire southern sky every few nights with a field of view covering 40 times the area of the full moon per image. Its sensitivity and cadence will catch interstellar objects much earlier and much more frequently than current systems. Estimates suggest Rubin could detect one interstellar visitor per year, maybe more, depending on the actual density of these objects in the local neighborhood. That detection rate turns interstellar studies from a once-in-a-decade lucky break into a regular observational program. Patterns will emerge: size distributions, compositional trends, trajectory alignments. All the statistical data you need to start building real models instead of guessing based on 3 examples. Wait for Rubin to flag a target, calculate intercept, burn engines, arrive months later while the object is still inbound or near perihelion, deploy multiple subprobes to image from different angles simultaneously, grab spectra, maybe even impact the surface and analyze the ejecta. That mission profile was science fiction 10 years ago. Now it is funded, designed, and on the launch manifest. The reason it works is because detection has gotten good enough to provide lead time and trajectory precision. 3i Atlas proved that, caught at 670 million kilometers with 5 months' notice before perihelion. Tracked by 31 observatories within 48 hours. Trajectory refined to sub-kilometer accuracy by Mars flyby. That is the baseline future missions need. If Comet Interceptor gets assigned an interstellar target, it will be because telescopes like Rubin and Atlas spotted it early enough to make the math work. It is just normal celestial mechanics, plus really big numbers. Escape velocity from the Milky Way at our location is around 550 kilometers per second. 3i Atlas is moving at 61 kilometers per second relative to the Sun. That is well below escape velocity, meaning it is still bound to the galaxy, just like every other star and planet. It is just not bound to our Sun. It will drift through interstellar space, get nudged by passing stars every few million years, and eventually either fall into another star system or get kicked out into intergalactic space by a particularly violent stellar encounter. The odds of it hitting anything are effectively zero. Space is big, really big. A comet 5 kilometers across, traveling through a galaxy 100,000 light-years wide, has approximately the same chance of hitting a star as a grain of sand dropped into the Pacific Ocean has of hitting a specific floating buoy. It does not happen. What does happen is gravity bends trajectories without contact. 3i Atlas has been bent by thousands or millions of gravitational interactions over billions of years. Each encounter changed its speed and direction slightly. The cumulative result is the trajectory we observe today. Fast enough to escape our Sun, slow enough to stay in the galaxy, angled across the ecliptic. None of that requires intent or design. It just requires time and statistics. The live stream tonight is your chance to see one of those statistical outcomes live. Not a recording, not a photograph. Live photons captured in real time and piped to your screen with a 13-minute light delay built in. The Virtual Telescope Project has been doing these streams since the early 2000s, back when live astronomy feeds were rare and bandwidth was expensive. Now it is standard. Gianluca Massi has streamed comets, asteroids, meteor showers, eclipses, and planetary events to millions of viewers worldwide. His setup in Manciano uses multiple telescopes ranging from small refractors to larger Schmidt-Cassegrains, all mounted on robotic tracking systems that can be controlled remotely via internet. The software handles pointing, focusing, and exposure automatically. The operator just queues up the target coordinates and lets the system run. For 3i Atlas, that means locking onto the predicted position in Virgo, starting exposures around 4:15 a.m. local Italian time, and streaming the results as they come in. Clouds kill the show. Equipment failures kill the show. But if the weather holds and the hardware cooperates, you get to watch an interstellar comet drift across the screen in near real time. That is the whole pitch. No hype, no alien speculation, just astronomy. The NASA press conference tomorrow operates at a different scale. Multiple spacecraft, multiple instruments. coordinated observations from Mars, Reconnaissance Orbiter, Hubble, Webb, Sphere-X, Swift, and possibly Mars Express, ExoMars TGO, and JUICE, depending on what data processed in time. The conference will feature scientists from different missions explaining what they saw and what it means. Expect technical details about nucleus size constraints, coma composition, dust grain size distributions, gas production rates, non-gravitational accelerations measured through positional residuals, and comparisons to Borisov and solar system comets. Do not expect definitive answers on the weird stuff like the nickel signature or the energy output discrepancy. Those require more modeling and probably more observations that have not happened yet. What you will get is the highest resolution imaging ever captured of an interstellar object, released publicly so independent researchers can analyze it. That is the win. More data means better models. Better models mean better predictions for the next one. By March, when it passes Jupiter at 54 million kilometers, it will drop below 15 and out of reach for most backyard setups. Professional observatories with large apertures and sensitive detectors will keep tracking as long as they can. Hubble might grab a final image in late 2026. Webb could extend observations even farther if the science case justifies the telescope time. Eventually, though, 3i Atlas will cross some threshold where the signal-to-noise ratio collapses and further observation becomes impossible. The comet will continue its journey unobserved. Billions of years from now, it might pass another star close enough to get perturbed again. Or it might drift forever in the cold dark between stars, a frozen relic slowly accumulating more cosmic ray damage until its surface is as black as charcoal and its volatiles are long gone. No way to know, no way to check. It will leave our field of view and never return. Watch it live or watch a recording later, but either way, you are seeing something that will not repeat. The specific configuration of Earth, Sun, telescope, and comet that allows Gianluca Massi to point a robotic telescope at Virgo and catch 3i Atlas drifting across the sensor will never happen again. The light captured tonight is unique. The photons streaming through fiber optic cables to your screen traveled for billions of years from some unknown origin point, reflected off a nucleus that formed around a different star and are about to terminate in your retina or your monitor. Pixels. That is the chain. Formation around another star. Ejection. Billions of years drifting. Interception by our solar system. Discovery. Observation. Livestream. You. End of chain. The photons stop with you. No more bounces. No more journey. They hit your eyes and convert to neural signals that your brain interprets as a faint, fuzzy gray blob moving across a black field. That is 3i Atlas. That is what interstellar looks like. Not dramatic, not cinematic, just real, cold, measured, documented. The coma might resolve as slightly elongated if the seeing is good. The tail, if visible, will trail off to the northeast based on Massi's November 11th observation. The anti-tail, if it shows up, will point east-southeast. Background stars will stay fixed unless atmospheric turbulence blurs them into streaks. 3i Atlas will move. That motion is your confirmation. Everything else is frozen. Stars, galaxies, static noise. Only the comet drifts, because it is the only thing close enough and fast enough to show parallax over the exposure window. That is the signature of a solar system crosser. That is what you're paying attention to. Not the brightness, not the color, the motion. The fact that it moves proves it does not belong to the fixed background of distant stars. It belongs to the here and now, the local neighborhood. The stuff inside 50 astronomical units that still responds to the sun's gravity before escaping forever. NASA's image release tomorrow will show the same object from a different angle, captured 6 weeks earlier when it was much closer and more active. Comparing the two data sets, tonight's live stream and tomorrow's high-rise frames, will let astronomers measure how much the coma shrank or grew between October 3rd and now. Shrinkage means activity dropped after perihelion as expected. Growth means something is still driving out gassing, possibly subsurface pockets of volatiles that got heated through thermal conduction and are now venting delayed. Either answer refines the model. Either answer adds data points to the limited sample size we have for interstellar comets. 2 objects is anecdote. 3 objects is the beginning of statistics. 3i Atlas is that third data point. The one that starts turning speculation into science. Scientists push back with data. Hype fades. Serious observations continue. A few outlier voices keep pushing the alien angle because it generates clicks and speaking fees. Most astronomers ignore them and get back to work. By the time the dust settles, you have a solid set of peer-reviewed papers in the Astrophysical Journal, Nature Astronomy and Astrophysics, laying out composition, trajectory, size estimates, and activity rates. Those papers become the baseline for future comparisons. 20 years from now, when Rubin Observatory has detected 50 interstellar objects, 3I Atlas will show up in the introduction section as one of the early, well-characterized examples. That is its legacy. Not a mystery, not a controversy, just a data point. A good, clean data point with solid measurements and multiple independent confirmations. That is what science runs on. Not hype, data. Tonight at 11:15 p.m. Eastern, Gianluca Massi will start the stream. Weather permitting, you will see 3I Atlas drift across the field of view over the course of an hour or more, maybe longer if he extends the observation window. The stream will probably include audio commentary from Massi explaining what you're seeing, pointing out background objects, noting any atmospheric interference or technical issues. He has done hundreds of these streams. He knows how to read the visual cues. Bloated star images mean bad seeing. Streaked stars mean tracking errors or windshake. Sharp stars with a fuzzy blob that moves between frames means good data. That fuzzy blob is 3I Atlas. That is the target. That is what everyone came to see. Not because it is spectacular, because it is real. Because it is from somewhere else. Because for a brief window of a few months, we get to watch it pass through before it leaves forever. That window is closing. December will be dimmer. January dimmer still. By spring, it will be a faint dot only professionals can track. By next summer, it will be gone. Tonight is one of the last good chances for anyone with a telescope or an internet connection to see it clearly. All bundled into a single press conference with scientists from multiple missions presenting their results. The data will be dense. Expect graphs. Expect false color images with wavelength keys. Expect error bars and confidence intervals. That is how you know it is real science and not a dog and pony show. Real science quantifies uncertainty. Real science shows you the noise floor and explains why the signal rises above it. Real science does not give you clean answers. It gives you constrained answers with statistical significance and reproducibility. 3. I Atlas will not be the dramatic reveal some people are hoping for. It will be the slow, methodical unpacking of what we learned and what we still do not know. That is the conference. That is what NASA does well when they are not locked down by government shutdowns and bureaucratic nonsense. If 3I Atlas is a typical interstellar comet, then we can expect future visitors to show similar compositions and activity profiles. If it is an outlier, then the diversity is higher than we thought and we need more samples before we can generalize. Either way, detection systems improve. Rubin comes online. Intercept missions get green-lighted. The European Space Agency, NASA, and other agencies start planning rapid response protocols for when the next one shows up. Maybe by 2035, we will have a standing fleet of small probes parked in heliocentric orbit, ready to chase any interstellar target that gets flagged. That is the trajectory. From 0 detections before 2017 to 3, confirmed by 2025, to routine observations and intercept missions by mid-century. 3I Atlas is a step in that progression. Not the destination, a step. One more piece of the map filled in, one more unknown converted to known. That is how exploration works. You do not leap to the finish line, you walk, step by step, object by object, data point by data point, decade by decade. The comet does not care. It will continue its path, regardless of whether we watch or ignore it. The only difference our observation makes is to us. We learn something, we refine our models, we prepare for next time. 3I Atlas gets nothing out of the deal except a name and a designation in the Minor Planet Center database. That is the exchange. We take data. The comet takes nothing. But the data we take feeds into every future calculation about interstellar object flux rates, size distributions, compositional norms, and trajectory statistics. Every data point reduces uncertainty. Every observation tightens the error bars. That is the value. Not drama, not spectacle. Just incremental improvement in our understanding of what is out there and how often it comes through. So tonight, you can watch a live stream from Italy showing a comet from another star drifting across Virgo. Tomorrow, you can watch NASA scientists present the sharpest images ever captured of that same comet taken by spacecraft at Mars. Both events are real, both are documented, both will be archived and available for anyone to review. No secrets, no cover-ups, just astronomy done in public with public data and public discussion. That is the standard. That is what makes science different from speculation. Science shows its work. Science publishes raw data. Science invites criticism and replication. If you think the high-rise images show something NASA missed, download the files and run your own analysis. If you think the live stream tonight is faked, build your own telescope and point it at Virgo. The data is public. The methods are public. The conclusions are provisional and subject to revision. That is science. That is how we figure out what is actually happening instead of what we wish was happening. Frozen gas and rock ejected from some planetary system billions of years ago, drifting through interstellar space until our sun's gravity bent its path into a hyperbolic flyby. We detected it, we tracked it, we measured it. Now it is leaving. The story is simple. The data is complex, the implications are significant but not earth-shattering. We live in a galaxy full of stuff. Some of that stuff passes through our neighborhood. We are getting better at noticing when it does. That is the takeaway. Not aliens, not doom, just better detection and better science. The live stream tonight and the press conference tomorrow are proof that the system works. Telescopes find things, scientists study them, data gets released. The public gets informed. Repeat, that is the process. That is what happened with 3I Atlas. That is what will happen with the next one, and the one after that, and every interstellar visitor we detect for the rest of human history. Watch tonight if you want to see it live. Watch the NASA conference tomorrow if you want the high-resolution details. Either way, you are witnessing the end of an era where interstellar objects were myths, and the beginning of an era where they are routine. 3I Atlas is not special because it is alien. It is special because it is the third. The first was shocking. The second was confirmation. The third is the start of a trend. By the time we hit 10, it will be normal. By the time Rubin detects 50, it will be boring. That is progress. Mystery becomes data. Data becomes routine. Routine becomes infrastructure. Infrastructure becomes the foundation for the next leap. That is how we build knowledge. One comet at a time. One observation at a time. One live stream at a time. The November 18th live stream is not the end of the 3I Atlas story. It is a midpoint. The comet was discovered in July, observed intensely through October, went behind the sun, re-emerged in November. Tonight, we watch it drift. Tomorrow, NASA releases Mars data. December it fades. January it dims further. March it crosses Jupiter. Sometime in 2026, it will drop below detection threshold and vanish, but the data will persist. Papers will be published through 2027 and beyond as researchers dig into spectroscopic details, dust modeling, trajectory refinements, and compositional analysis. Some grad student somewhere will write a dissertation chapter on 3I Atlas, comparing it to Borisov and Oumuamua, looking for patterns that might predict what the next interstellar visitor will look like. That dissertation will cite tonight's live stream and tomorrow's NASA data release. The chain continues. Observation becomes publication. Publication becomes citation. Citation becomes foundation. Foundation becomes the baseline for future work. That is how science builds, incrementally, collectively, publicly. Know that you are looking at something that traveled farther and longer than any human artifact will travel in your lifetime. Know that the light hitting your screen right now started its final leg 13 minutes ago, bouncing off a nucleus carved from the debris of another star's planetary formation. Know that this is as close as we get to touching another solar system without leaving our own. That is 3I Atlas. That is tonight. That is the live stream explained without the hype. Just photons, physics, and the slow patient work of figuring out what is actually out there in the dark.